All right, y'all. So today I'm going to show you how we describe waves by their shape, their size, and what they're doing. Little review from yesterday. We talked about how every wave that's out there can be classified whether or not it needs a medium or a material to travel through, and all the ones that fell in the mechanical family do, or whether the ones that can go through empty space and the ones in the electromagnetic family can do that. We can also talk about their propagation method or the way that they wiggle. And so when we see a wave that travels this direction, but whatever is causing it to vibrate, causing the wave vibrates perpendicular to that, because these two wiggle and wave are at cross directions or 90-degree angles to each other, we call that a transverse wave. When the thing that's wiggling or vibrating is moving in the same direction as the wave, we call that a longitudinal or a compressional wave. And one of these is certainly a lot easier to draw than the other. So here's a regular old slinky or a rope or something like that. To draw a transverse wave, all I have to do is this. If here's this normal looking slinky like this, to represent a longitudinal wave, there'll be spots where it's really spread out and then bunched up for a bit and then spread out and bunched up for a bit. Way easier to draw transverse, so I'm just not even going to mess with the longitudinal ones. All right, so we have to be able to describe these waves in numbers, their size, their shape, what they're doing, how they're traveling, etc. And we're going to start by looking at what would be required to just describe one wave. The first thing that we would need to do to describe this, if I needed to tell somebody how to draw this or how to replicate this thing, would be to describe the actual length of this wave. Now, one wave is one full up, down, back and forth. It's one full cycle that looks like this. And so on this diagram right here, we could represent this with starting from the going up, down, up like this. You could also say, no, we're going to start from the very tippity top, come all the way to the bottom, come all the way back up to the top. You could represent this by saying, no, I want to go down first, then up, and then back down. As long as it covers all the parts of the cycle right there, that's one full wave. And so don't measure, from here to here, that's only half of it. So the length of this thing is super important. We'd actually have to describe how far it reaches along the length of the medium that it's traveling through, whether it's the water or earthquake wave or, in a slinky. The second thing that's going to be super important for a transverse wave is going to be the height of it. We don't really have a height for longitudinal waves, but we'll worry about how we're going to measure their size later. For now, I need to describe the height of this wave, and it sure seems like it would be obvious to say, well, the top and the bottom are this far apart. That's not how scientists do it, though. The way we're going to describe the height of the wave is to describe how far did it stretch, or how far did it displace from its original position. So that's the height that we're going to use to describe the wave, not the full one. And because these things are usually symmetric, you can measure from the middle up to the top or from the middle down to the bottom like so. Either one of those is fine. But that's it. For one solitary wave, that's all you would need to do to describe it. And so we're going to play with this simulator later, and we could use a ruler to come over here, and it turns out that this thing has a wavelength of about 4, and it looks like it has a wave height of roughly, I don't know, what is that, a little bit more than half, maybe 0.6 or something like so. If you were to make these waves a lot skinnier, you would expect this wavelength obviously to get skinnier. Move out the way, and it looks like this is, I don't know, 2 point something. That's it, though, to measure the length and the height of a wave, and the vocab for that is pretty darn simple as well. The length of one wave is a concept known as, big shock here, wavelength, right? And this is just describing the length of the silly thing, and the symbol for this, it's a length, and so we're going to accentuate the fact that it's a length by using an L to represent it, but it's a very, very specific L. It ain't a regular old English L. It's going to be a very specific L to let us know that it's talking about a very, very specific length, and that's this Greek letter called lambda. To see this thing spelled out like so, maybe sometimes you won't be able to type this symbol without importing a Greek keyboard. It kind of looks like somebody drew a capital X and then just erased 3/4 of it. Or it looks like somebody really doesn't know how to draw a giraffe and they tried it. But it's a length, and so we're going to measure this thing, we're going to describe this thing in meters, which of course you can always abbreviate with lowercase m. As far as measuring the height of this thing, I'm going to do purple or pink. I went pink. To measure the height of this thing, I'm going to put a little asterisk on here because there's a different way that we're going to do this for compressional longitudinal waves. Don't stress about that. This is a word called amplitude. And all this is really measuring is how much energy is stored in one mechanical wave, right? Like if you're standing here on the beach and you see this wave coming at you, that's very different than seeing, that's the worst tidal wave I've ever drawn. That's very different than seeing, that's even slightly better, that wave coming at you, right? The height of this thing is going to determine how much energy it's carrying if it's transverse. If it's longitudinal, we'll worry about that later. But because it's a height, we're gonna measure this in meters as well. And the symbol for this is just going to be a capital A. Again, this is just going to be for transverse. For longitudinal waves, it's something different. All right, so that's just a wave, but that doesn't have anything to do with how it's moving or how it's being generated. So if there's a whole bunch of them that are moving, we're going to need some other things to describe this. One of the things that we're going to use to describe this wave as it's moving is how fast it's actually moving. Let me slow this generation down a little bit. How fast it's actually moving left to right, whether it's covering the distance pretty quickly or whether the wave peaks, called crests or bottoms, troughs, are actually going very, very slowly. And so just like we did this in kinematics where we describe how fast something changed its position, how fast it traveled through space, we're going to do that same thing with waves. And this is not a big surprise either. This idea of how fast it's traveling through space right there, known as the speed of this wave, or of course, fancy term for speed, velocity. And what this is describing is, of course, how fast it moves through space, lowercase v, and this is just like in kinematics and energy, meters per second, which you can abbreviate m/s, all lowercase. All right, so we have measures here of how big this thing is. We have a measure of how fast it's traveling through space. The other two things that we're going to use to measure this wave are really just describing it in two different ways. We can talk about how fast a ball is being thrown. We could talk about how big a ball is. We can talk about how wide a ball is or how long it is. With waves, though, because we're making lots of them, the other thing that we would need that we didn't need with just throwing an object is how often they're being generated. So if you look at this little piston thing on the left and it's going up and down a certain number of times per second, and we could say, well, maybe this wave is being generated less often, and this wave is being generated more often, less often, more often. The idea of oftenness is going to show up quite a bit. Let's see, I've done yellow and pink. We'll do this one in blue. That's highlighter, sorry. The speed that it actually travels down, and then also how often it's being generated. And there's two ways we're going to describe that. Way number one is simply going to be a concept called frequency. And frequency, I can spell this, frequency is just going to be the number of waves per second. And you know what it means to do something frequently. If I said, how frequently do you brush your teeth? You'd say 2 or 3 times a day. Or how often do you go to sleep? Well, once a day, maybe twice a day if you take a nap. We're describing the number of times that something happened per time. Now, waves per second is a lot, and so we've given this thing a nickname, and we named it after a scientist by the last name of Hertz. And 1 Hertz, abbreviated capital H, lowercase z like this, is equal to 1 wave or 1 thing per second. So 1 1,000, 2 1,000, 3 1,000, that's a 1 Hertz clap. 1 1,000, 2 1,000, 3 1,000, that's 2 Hertz. 1 1 10, 1 10 10, 1 2 3, 1 2 3, that's 3 Hertz, so on and so forth. I'm gonna put that on here. Frequency. Cool, I didn't even spell it wrong. Both of these guys right here are going to be measuring how often the wave is being generated. Frequency is one way of doing that. The symbol for this is a lowercase f. Sometimes you'll see it written as kind of a fancy cursive-y looking script f. I'm a-okay with just a lowercase regular old f. It doesn't really matter. But you can describe this as either the number of waves per second, or you can describe this as hertz, or you can use the abbreviation for hertz, which is capital H lowercase c. Why capital? Because it's a proper name. It's named after a person, and that's a proper noun. The flip side, the way you could do this would be, instead of describing how many waves per second are being made, you can describe this as the number of seconds that pass in between each wave. And this is a concept known as the period of a wave. Period just means length of time. Your third period is 85 minutes long. The Jurassic period, right? Like all of this means just a certain amount of time, seconds in between wave. So if I'm doing a, let's just say, a 2 Hertz wave, so 1 1,000, 2 1,000, 3 1,000, what that means is that there is going to be 1 second every 2 waves, and so the period of that thing is going to be 0.5 seconds or 0.5 seconds per wave. Frequency and period are just reciprocals of each other. If you know one, divide the other one by 1, and that gives you the other. So the final wave variable is really just the same way of saying frequency, just kind of in different letters. Period is going to be measured in seconds. You can also say seconds per wave. Either one of those is fine. And it's a time. And since it's a time, we're going to use a t. But just like we didn't use a regular L for wavelength to specify that it was a specific length, we're not going to use a regular T for period. It's going to be a capital T that specifically says this is a special, specific time, not just generic old T. So let's look at some example problems on here. Girl shakes a slinky 8 times in 2 seconds. So we have number of waves in time. That's talking about how often this is going down. One way you could describe this would be to say the frequency. And in this case, her F is a certain number of hertz. 8 shakes in 2 seconds is going to be 4 waves per second, or 4 hertz. The other way you could describe that would be the period of this wave, and this is going to be measured in seconds. You can say seconds per wave, but that's just kind of implied right there. 2 seconds divided by 8 shakes, 8 wiggles, 8 waves, whatever, winds up being a quarter. You could also do this in decimal and say 0.25 seconds per wave. The amount of time that passes between each wave, or how many wiggles or how many waves this person is making per second. All right. This one right here is describing how far this thing actually moved in a certain amount of time, which is going to be the velocity. And in this case, v is going to be a certain number of meters per second. If it goes 20 meters in 4 seconds, that is a velocity value of 5 meters per second, or a fast run for a teenager. This last one on here is talking about how many waves and how much distance. It's describing how long they are. And so this is going to be wavelength, and the lambda is going to be a certain number of meters. And it turns out that 5 meters per wave, or per 40 waves, means these things have to be pretty small. Don't say 8. They can't be 8 meters long. You have to fit 40 of them in 5 meter sticks. And so 5 over 40 is, of course, 1/8, or you could say 0.125 meters. Either one of those is just fine. So just like with circuits, there's a lot of variables here. I've got a practice quiz for you. You guys are going to knock out a concept builder, and then we're going to do some test corrections. You got your variables quiz next week. There's a practice quiz that'll be online. I wish you the best of luck.